Here's an ice chart where we have a reaction A plus 2B makes C, and we're given a Kc value that's extremely large, 1 times 10 to the 26. That large value of K tells us this reaction is going to make a lot of products. When this reaches equilibrium, we're not going to have very much of the reactants left, and we're going to have mostly all products. The problem is we're starting the reaction completely opposite. We're starting it with all reactants and no products. If we tried to do our normal ice chart and we said the product side's going to increase, the reactant side's going to decrease, we're going to lose X, lose 2X, gain X, we're going to 0.3 minus X, 0.01 minus 2X, and X. We would then set this equal to Kc. 1 times 10 to the 26 would be the products divided by the reactants. And we know that a large value of K means the numerator will be large at equilibrium and the denominator will be small at equilibrium. If X is a large value, we can't use our assumption method to make the math any easier. We can't do any approximations. We can't do the quadratic formula on this because the highest power of X, if you multiply all this out, is going to be the third, X to the third power. So in order to solve this ice chart, what we're going to do is drive the reaction 100% to the right. We're going to drive it completely to the right because we know the reaction is going to end up very close to the right-hand side, almost completely. So we're going to write an ice chart that shows this reaction being driven 100% to the side where the equilibrium is going to end up. So we went back to the initial row. Now, this involves the stoichiometry that you have to figure out your limiting reactant based on the initial concentration and the coefficients. And in this case, the limiting reactant will be chemical B, which means when the reaction goes completely to the product side, all of the B gets used up. Chemical A is also going to react away, but the 1 to 2 ratio between A and B means we lose 0.005 instead of 0.01 like we did for the B. So we're going to end up at 0.295 for the concentration of A. The concentration of C is going to increase by positive 0.005. But if we look at our ice chart at this point, we know we can't be at equilibrium because chemical B has reacted away to 0. We can't have an equilibrium where we have no concentration of the reactant because that would mean the forward reaction stopped. Therefore, what we're going to do is write an ice chart that shows the reaction going back to equilibrium. So we're going to take the end of the first ice chart, and then we're going to show what happens to the concentration of the chemicals. Chemical C has to react away a little bit. Chemical B is going to increase a little bit, and chemical A is going to increase a little bit. Now we can solve this ice chart much more easily for K because our Kc value, 1 times 10 to the 26, equals 0.005 minus X divided by 0.295 minus X times 2X squared. This time, because we drove the reaction close to equilibrium, and we know that a large value of K means we have a big number in the numerator, small number in the denominator, this time the approximation method will work. Because the only way that the numerator can be large is if 0.005 minus x is approximately 0.005. So we can neglect the x in the numerator. We can also neglect the x being subtracted from 0.295 in the denominator. The other term is 2x squared, which has no addition or subtraction, so we can't do the approximation because there is no addition or subtraction. Now the math is a lot easier to solve for x. We get x 6.5 times 10 to the negative 15th. That's very, very small compared to the initial number. It's definitely less than 5%, so the approximation method works. And we can take this answer for x and substitute it back into the ice chart to find all the chemicals' equilibrium concentrations.